Hi, Gabby. Hi, everyone.
Hi, everybody.
Hi. So do you need help streaming live? Oh, you are.
Yes.
Okay.
The streaming. Okay, now it's working.
Okay.
Thank you so much.
Sure. Sorry, I'm late. Hi.
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 Yes, so, okay, so can we start now? The only thing is that I just need to check again if sound is going to be shared. Okay, so let's just do a little test to see sound is the sound being shared?
No, not
No?
yet. No, you have to do that
Okay.
again.
Then, okay, then.
So when you share screen, when you're going to choose the screen, you need to click two little boxes at the bottom of that message that says sound and audio optimization, like audio and video.
Sorry?
When you press share screen,
Yes.
if you do it again,
Share screen? Yes.
at the bottom, it has two little check boxes.
A little. Sorry.
You need to, can you stop sharing and then, yeah, and then share again, please.
Oh my God. I'll share. You share. No. Stop share. Okay, now I got it. So I share screen again, right? Oh, here it is. Share sound. That's it. Okay. Okay, so yeah, so maybe we can just start and yeah. Sorry everybody about all the messing here with the controls. So we can finally start. Hi everybody, my name is Gabi Celani. I'm from the University of Campinas, and I would like to introduce you to the other host of this session, Marcela Noronha. Marcela, can you just say hello?
Hi everybody, thanks for coming.
Yes, and yes?
No, go ahead.
Yeah, so we're going to start this session, which is in which we're going to start with Ibrahim Postinci. And is Ibrahim here? Yes? Is Ibrahim here?
No, I don't think he's coming. He didn't. He said he probably wouldn't be able to come.
Okay, then maybe we start with Yang Song. Yang is here, right?
Yeah, hi.
Okay, so we're going to present your video.
Yeah.
Okay. So it's video, this one, right?
Hello everyone, my name is Yang Song, a practice-based PhD student at the Center of Architecture and Visual Arts, CAVA, the School of Architecture, University of Liverpool. The research title that I'd like to present today is AR Robot, the AR-assisted robotic fabrication system for parametric architectural structures. My research project tries to assist the robotic fabrication process for parametric architectural structures with augmented reality AR technology to explore the new possibility for easy architectural robotic operations. Due to the lack of computer programming skills and the disconnection between design and fabrication, architects are hampered in the robotic operation process. Robotic operations traditionally need specific experts computer science and programming knowledge to program the complex movement. Even though robotic errors occurs beyond the simulation occasionally in the physical operations, the screen-based simulation is out of touch with the real physical world. This process is dangerous because workers are in the same space as the moving robotic arm. So we are using the AR-assisted robotic operation method to reduce the complexity of the traditional coding-based operation method and avoid dangers in the physical operation. So in this paper, we will use a UR10 robotic arm in combination with iPhone 11 and Microsoft HoloLens 1, as well as in terms of software, Rhino, HAL Robotics, and Hologram plugin in Grasshopper to demonstrate a new kind of applications and workflow. We got 3 tests in our paper to solve the problem and upgrade the workflow for today's architecture and construction industry respectively. Test 1 is augment visualization of robotic data and on-site environment. Explore the possibility of using the AR to visualize the corresponding holographic information of the on-site robotic by showing virtual holograms upon the real objects, as well as the opportunity of using the AR device to recognize the uncertain on-site environment by scanning the 3D space in real time and spatial mapping the location information. Besides, we use the device location recognition, on-site holographic information, and the QR code identification method to give the designer and operators more intuitive information and experiments about the robotic arm operating. Test 1 shows that AR-assisted robotic data information visualization could help designers, especially the unskilled users who lack the corresponding operation experiments, understanding the robotic arm better, including its corresponding information dynamically. Furthermore, the AR-assisted on-site environment cognition method could help the robotic arm recognize the reachable surroundings to its data information to avoid collisions and dangers while taking the actions in an uncertain on-site environment. Test 2 explores the possibility of using the AR technology to realize robotic trajectory planning and optical avoidance, instead of using the traditional method, programming by computer science language or demonstration, for architects who lack the corresponding knowledge. To do this experiment, we use the device location recognition and arc marker tracking method to digitize the physical optics for robots to avoid and generate new paths. The user could point out the location along the trajectory in the entire operation area. Moreover, the physical location nodes would be converted into the digital tool central point TCP commands for robotic plugin to identify and calculate to operate the route in AR environment. And the virtual robotic arm simulation animation will be shown as holographic through the AR overlapping the real machine. For optical avoidance, the user can scan the arc marker to convert the physical optics into digital data for robotic plugin to calculate the collision avoidance robotic trajectory. Test 2 demonstrate that this AR-assisted robotic trajectory planning method provides unskilled user with intuitive simulation in robotic path planning and translate human actions directly into robotic programming language. Moreover, the AR-assisted optical avoidance system can digitize the physical optics along the robotic trajectory and send them to related software for real-time trajectory calculation to avoid physical collisions and dangers during the operation of complex construction process. Test 3 is AR-assisted robotic fabrication operation system. We start with a simple robotic operation, pick and place, and we choose the stack a foam break column from bottom to top. First, the user can scan the QR code to locate the physical robotic arm and the console decks with the AR hologram. Second, the user is required to tap the virtual break hologram in the prepare area and the target area. Next, The command would be sent from the AR device to the robotic plugin, and at the same time, the user could preview the whole robotic holographic simulation and safety area that they need to maintain from the robotic arm operation radius in AR to keep it safe for the later physical operation process. Last, after all the simulation ran safely and successfully in AR, the user could start the physical robotic operation process through AR interface. Test 3 shows that it is a safer and more efficiency process to operate the robotics through AR-assisted method with the onset gesture command and holographic trajectory simulations. All the computer science programming techniques has been pre-coded in Grasshopper. The user simply need to point out the preparation and the target location instead of programming in computer science language. In conclusion, the AR robot project bridged the gap between architects and robotic fabrication. This AR-assisted system makes design and robotic fabrication in the hands of architects who lack the computer programming skills and experiments but full of architectural inspirations. Further work would be developed of using more professional space detecting and scanning sensor to assist the AR to translate and recognize the uncertain on-site environments for robotic software calculation. Through the AR-assisted real-time environment, multiple robotic arm and operations will be developed for man-machine collaborative fabrication parts. More complex form of optical avoidance and more complex robotic operations will be created and completed during the whole AR-assisted system. And the final goal is to make the AR-assisted robotic fabrication workflow simplified and modified for architectural scale elements and applications. That's all for the presentation. Thanks for listening.
We can't hear you, Gabby.
Now you can. Yes,
Now we can.
Congratulations, Yang, for this very fine video. I especially congratulate you on the quality of the sound. It was really clear and very nice graphics. Congratulations. So, sorry, I forgot to say that we are planning to present all the videos first and then start the discussion at the end, right? So that people who are watching us on YouTube, they have the chance to write down their questions. All right. So let me see. Ebrain has not arrived, right? No. So
no, not yet.
Okay, then let's proceed with João Vitor, Leonardo, Vinicius, and Raquel. And Raquel is here. I can see her. And
Leonardo too.
And Leonardo as well. Okay, so I'm going to share my screen again and show you the video. So this is number 3, right? 283, right?
Yes.
Okay.
This is architecture in context.
Okay.
A database approach to optimize climate performance.
Can you hear the video?
It's a little bit low, but we can hear it.
Studying this topic, those he mentioned ended up being key
it's low for me
concepts
too.
on which we relied when we were building our research. Namely, the current production of hermetic buildings, database decision-making supported by parametric relationships, modularity as a mass customization and adaptability strategy, and convergence between digital manufacturing technologies and local builders' knowledge in the Global South. Which leads us into the objective of this research, that's to understand how to adapt an existing building to local environmental conditions based on the optimization of its climatic performance. To that end, we elected modularity, flexibility, and mass customization as guiding principles to the design, which we employed to follow on the development of a second skin proposal aligned with the use and context of the building and the study. Not only hopeful to reach a design that feasibly improves the facade aesthetics and climate performance, what we ultimately aim to achieve is a critical reflection on the adaptability of constructed buildings, focusing on the facade layer. The methodology of this research stems from design science research, or DSR for short, which concerned itself with the pragmatic research steps to the development of artifacts for solving specific human problems. This flowchart exemplifies how the methodology was applied in this research, in which we first understand and diagnose the problem to be addressed, then propose build strategies to address them, in this case a facade element to solar radiation, and finally evaluate the performance to either validate or rethink the design, much like the standard scientific method. The applications and plugins listed here were the tools that we chose for problem analysis in the design process in this project, namely SIGraDi, Grasshopper, Ladybug Tools, Edit, and ArchiCAD. Now onto diagnosis. Context analysis and adaptability gaps. The ideal passive thermal conditioning strategy for the local climate is permanent cross-ventilation. Shading is a fundamental strategy in most Brazilian cities, which must be applied when temperatures exceed 20 degrees Celsius. The main variable chosen to be addressed in this initial application study was solar radiation, but visibility and access to daylight were also considered. These were the main issues we identified in this stage. The building's implantation had one of the longest facades facing west. The recessed platforms do not protect the facades at certain times of the year. The manufacture of brise soleil has reduced efficiency. There is a lack of landscaping and tree planting. The installation of air conditioning condensers indicates that use and occupation conditions would be supported by a high investment in artificial-only air conditioning. Now then to the analysis results. The radiation study was executed considering an annual analysis period, and the result is the average incident radiation in kilowatts-hour per square meter, ranging in this case between 0 and 2108.26. The west and north facades are more susceptible to heat and should be protected. The high incidence of heat on the external walls and roof points to the necessity of both light and somehow reflective solutions for the envelope. Reflections of solar energy from the ground and surroundings were not considered in the analysis performed, due to the limitations of the tool chosen for the simulation. For the data-driven parameters, the first step was to reduce the complexity of the solution by designing simple vertical planes to cover the facades analyzed and using modularity as a basic principle, as the ease of documentation, manufacturing, and assembly could easily be assimilated by available technology and local labor. In these vertical planes, we create a fixed grid composed of cells which were assigned a remapped numeric value based on the categorization of the values outputted by the radiation simulator. Each segment of this categorization was assigned a specific color from a gradient, from blue for less radiation incidence to red, indicating more. Some of the grid cells close to the openings were assessed as a new category for light permeability, visual clearance, and also formal variation, and represented as the cleared panels. The main challenge for this solution was balancing shading and natural lighting without overprotecting and blocking the views, nor opening too much for solar radiation. Each category, represented by the colored panels seen in the previous slide, was designed with the intention of receiving a family of modules designed by associating a common and affordable type of ceramic block in a standard frame. The module families were proposed on two main criteria: permeability, varying the number of existing blocks within a single module, and formal disposition, related to the organization of the blocks within the module itself. In addition to both financial and accessibility justifying this choice, the use of bricks also refers to the materiality of ceramics in the culture of Latin American construction, used since colonial times and still frequently seen in houses and settlements as a constructive element. The algorithm can generate a series of iterations which can vary according to priorities and negotiations between the participants in the design process, whether architects, customers, or investors. Parameters such as cost, complexity, aesthetics, available tools, and the number of other issues can influence the project approach and hence the chosen module pattern. Regardless of the options chosen as the final result, the iterations share the ability to absorb a significant fraction of the solar radiation incident on the building. functioning not only as an effective and inexpensive shading solution, but as a distinct second skin that uses the characteristics of the original building and its surroundings as formal inputs. This is evidenced by comparing both simulations before and after the implantation of the second skin. Notice how the incidence of the direct radiation on the west facade significantly decreases. The core aspect of the proposed artifact matches one of the main mass customization features, modularity. It associates variety with some degree of standardization, which can be adjusted according to previous established objectives, such as desired permeability, technology, conditions of the local workforce, financial feasibility, among others. The future work may comprise a deeper level of information, embracing the study of the relationship between design and execution, like concerns about materiality as well as artisanal and digital construction issues. That's it. Thank you for watching.
We can't hear you again.
Sorry again, because I'm turning off the microphone on the physical button. So congratulations, Raquel and Leonardo, on your presentation. It was a bit low for me. I hope you were able to understand it. Was it okay? Yes. Could you hear it? The presentation?
Yes.
Yes.
Yeah,
okay,
it was
great.
Low but hearable.
Yeah. Okay. It was, but this is a very nice new approach to a very classical problem, the facade shading problem, which is very, I mean, it's something very important for the tropical climate. So congratulations on that presentation. And we still don't have Ibrahim, right? So we proceed to the last one, which is, sorry, let me just get the...
Theodore Dunas.
Theodore, right? Theodore Dunas. And Theodore is here, right?
Yes, he's here.
Yes. Okay. So this one.
Hello, my name is Theo Dunas, and I'm here to present a paper from the arcchain.cc project, a project I've been working with Vasim Jabi from Cardiff University and Davide Lombardi from Sinayatom Liverpool University. The paper we're presenting today is concerned with non-fungible building components using smart contracts for a circular economy in the built environment. Our motivation to work within this particular area has emerged from a view that looks at the architecture, engineering, and construction industry as a fragmented, unproductive, and adversarial industry. Within the IAC industry, you have a lot of smaller players that essentially are coming together to create a project every time you have to design and construct a building. And research has also shown that in about 30 years, globally, the AEC industry hasn't been increasing its productivity by more than 1 or 2%, which is really low compared to other industries, such as the manufacturing industry. At the same time, a lot of the processes within the AEC industry are seen as adversarial, passing liability down the line and in the next phase of the project, rather than trying to have an integrated approach as much as possible. One of the major problems that we have at the moment within the industry is the issue of circular economy and the amount of waste that the industry is producing. We are certainly knowing that part of the carbon mitigation and climate adaptation that we will need to do needs to focus now on the embodied carbon stage, essentially because we have already found really good ways to optimize the carbon impact in terms of the energy performance of buildings, shifting out the attention to embodied carbon. And we know also that carbon efficiency comes from a really tight supply chain integration, where you remove any kind of friction from the supply chain in terms of building components. Building information modeling was a possible solution and certainly has improved processes compared to the past, but at the same time, it doesn't bring any kind of radical improvement in terms of embodied carbon. It creates essentially a lot of complex models and also has no connection or interdependence on supply chains and no availability of carbon performance data. So part of the paper today is to showcase one way we could actually start providing better information on materials and building components from the beam states to the supply chain and back. We use essentially a blockchain, which is a universal state machine. It's a decentralized network that is able to execute code in the form of smart contracts. And within our example, we're using Ethereum as the blockchain and SIGraDi as the language for the smart contracts. We use the construct of a non-fungible token, which is essentially a unique digital identity that can be tracked through the blockchain smart contract. It can be owned, tracked, transferred, and so on and so forth. The smart contract acts as an NFT registry where you register the component, and then the data of the component rests with the interplanetary file system, which is a global distributed decentralized file system that can be accessed by everybody. Material within the interplanetary file system is always encrypted and addressed depending on its content, not its address. Here you can see the really simple smart contract that mints the NFT. The code is a little bit more complicated, obviously, but the function is really self-contained and easy to use. Now, our innovation comes from integrating TopoLogic with the app of TopoLogic that was created by Wasim Jabi and Robert Ace at Cardiff University that allows us to represent the building into a non-manifold topological representation. Essentially, TopoLogic within the screenshot you see runs on Virtual on Blender, so it runs on a visual scripting platform and allows us to completely represent the topology of a building, analyze it into its components. You see the structural system on the right-hand side. And this, we are able then to use the underlying Python and a Python script to essentially talk and discuss between the building model that runs on TopoLogic to the Ethereum smart contract, and essentially take the whole building representation and component by component, mint it on the whole Ethereum smart contract along with RPFS. So from that point of view, we are able then to also add on TopoLogic any kind of dictionary information that is carried by the building component, for example, materials or any other kind of properties that you might have. You see here a screenshot from the recent SIGraDi workshop that we're running in September, where we were able to do all of this completely graphically without any kind of need for running custom scripts from within TopoLogic. Hence, we were able to pass information from a building component and a material to a blockchain and record it there. Now, why is this important? Because essentially then on the smart contract, we can create material passports that will track not only the properties of the material and the component, but also their status in terms of where they are within a supply chain, but also where they are within a building. And from that point of view, we are able to create a building component cadastre for any kind of new buildings that are going to be created, creating essentially a system that is trustworthy, a system that is immutable, where we can always track components and create essentially the kind of global bank of materials from the buildings that are created. And through this really simple showcase, we've created an integration between supply chains and design applications. And hopefully one of the things that we will be able to build on top of this is monetary incentives where we could, for example, incentivize designers to use materials and components with a lower carbon footprint by tightly integrating the supply chain, the design, and the monetary incentives that go into the system. Thank you so much for your attention. Additional work from the SIGraDi Smart Contracts workshop is also credited to Felipe Brandao, which we thank so much. Thank you again, and I'm happy to answer any questions you might have.
Okay, so you can hear me now, right?
Yes.
Yeah. Okay, so congratulations, Theodore, for this nice presentation. Very interesting. I was very interested by the topic of creating these unique tokens for tracking materials and enabling or helping to create circular economy. Very, very interesting. Okay, so we still don't have Ibrahim, right? So Marcela, do you remember if we're supposed to share the video even if the person is not here? Or...
I believe so, yes.
Yeah, okay, so let's just run it and let's hope that he can still make it.
Hello, everyone. Good morning, good afternoon, and good evening based on your location. My name is Ibrahim Pustimci, and I'm assistant professor and the director and founder of the Robotically Augmented Design Rad Lab at Kent State University. Today, I'm here to present PX1 Switch, a kind of a physical robotic solution for real-time robotic controlling. With the growth of advancement and accessibility of tools and technological tools and platforms for everyone's use, the question of accessibility is really rising more than ever. One example would be the use of 3D printing that used to be an industrial kind of solution or mechanism that more and more kind of became available for everyone, and now everyone and cheaper, available and cheaper, and now everyone has something like this in their house or on their desktop, which is at the cost of availability, at the cost of losing some of the flexibility, they became more and more available for everyone. So for this specific project and patent, we are looking, or we have looked into the question of real-time robotic controlling. And the fact that when you're dealing with robotics and robotic kind of motion control and motion design, we would deal with software packages and kind of creating advanced programming solutions to make a real-time robotic motion. Or we would need to be present as a user within the physical world or physical setup, close to the teaching pendant to control it through a 3D kind of controller that is available for KUKA robots. And it's worth mentioning also that when we are talking about programming, something that a robotic specialist would imagine or would kind of deal with is something like this, which are lines of codes, and it's only a simple KRL code. And when we are talking about programming in our discipline, more or less creative disciplines, where we are more used to node-based programming and simpler interface. So it might be an interesting gap to fill when we kind of look into real-time robotic controlling for artists and kind of creatives. And that would need two fundamental requirements. One is really basically the knowledge of programming, because it mostly happens in a more advanced kind of programming setups. And the other is really a financial investment, either through developing a kind of a code or buying a code, or through kind of buying a software package from KUKA itself, which can cost from $3,000 to $10,000. So the problem is when these tools or these kind of platforms becoming more demanded in creative disciplines among artists and designers, which are interested in triggering an existing robotic program and controlling the robot motion in interactive real-time manner. Some examples of these would be the very kind of famous and familiar project named Box by Batandoli in 2013, where they create this installation or performance with kind of pre-programmed robotic arms and kind of an army or ensemble of those. Another example would be Nigel Stanford's Automatica 2017, which again is the same scenario. It's an ensemble of pre-programmed robots that are triggered or kind of their motion is triggered at the same time in real time. And one of my favorite examples is Black Flag's project, which is really looking into a simple robotic motion, but combined with this kind of fluidity of the cloth, is really producing this artistic setup. So the reason I put these quick references here, which are kind of completing the text in the paper, is really the fact that the robotic motion in art discipline is that it doesn't have to be extremely complicated or advanced. Rather, the idea of having it in real time, or the idea of making it performative is really the question. So the solution that I'm proposing here with PX1 switch, which is internationally filed patent, which was published internationally in 2020 and filed in 2017, is really the same question. So how we can really bypass some of these programmings, or how we can really bypass some of these costs of buying software packages and kind of like investing in those, by basically creating a hardware platform or hardware plugin for the robot controller that can sit in between of the user and the kind of the controller itself. So it really kind of bypasses the programming by creating a bridge, a physical bridge that kind of docks into the pendant or teach pendant of the robot, and makes it kind of more available for the user from any other open source software. It's very similar to some of these smart plug devices, like this one, for instance, that the plug is now augmented with another smart plug, and then you can control the smart plug from any other platform, like your cell phone or any other devices. So that smart plug makes the whole plug or outlet smart. And it's very similar to PX1 switch. So it sits in between with an easy and intuitive learning process, affordable and open source qualities, and easy to develop based upon. And it really kind of makes the pendant to be removed and to be smart by just this simple addition of kind of a servo-based off and on Boolean kind of button push and pull. So it is controllable through many other programming and programming softwares and design platforms such as Maya, Grasshopper, Rhino, Automax, Unity, and so on and so forth. And it's really kind of making it as simple as creating an off and on button in any of those softwares. It's made out of a plugin kind of scenario, a physical plugin scenario where the servo is controlled wirelessly or wired from remote kind of conditions, and it kind of pushes and pulls and controls the teach pendant through its kind of interaction with the pendant. And here are some diagrams of the scenario. The first iteration was just the proof of concept at its very basic limit, and that kind of again docks into the controller, but then it became more and more advanced and became a kind of the existing final iteration or version of the PX1 switch, which docks into a robot controller, the physical controller, and then sits in between and controls the robot through kind of a remote scenario. One example, we quickly did some proof of concept tests at Rad Lab. This is, for instance, controlling the robot arm and its motion through kind of a cell phone based scenario, which is kind of a simple MIDI controller, which you can just download open source. And another one is just a simple off and on scenario, from kind of Grasshopper, where you can add the motion or play the existing program in forward or backward, which again seems to be where some of those projects that I mentioned are taking advantage of robotic in kind of real time. We tested that as a demo in Rad Lab with a kind of a videography 3D scanning installation, which is further detailed in the paper. So I wouldn't borrow your time for that. And with that, I just wanted to conclude the whole thing with a kind of brief introduction that I made of PX1 switch, and thank you for your time and for your attention. Please stay safe and have a good day.
Okay, very nice presentation as well. It's a pity that Ibrahim couldn't make it, because I'm sure we would have a lot of questions. Very interesting type of interface. Okay, so Marcela is checking out if there are questions on YouTube, right?
No, yeah, but no questions
not yet.
For the moment.
Okay, so maybe I would like to start asking a question to Leonardo and Raquel, because you guys showed something that is, like I mentioned before, it's a very classical problem for the tropical areas in which we have a lot of sun and we need shading. And my question, but at the same time, since this is a very important and classical problem, it has been tackled in many different ways. So I wanted you to basically explain a bit of about what is that your project, your proposal has that is different from previous ways of tackling this problem of sunshade. So what is that you have that is really innovative in relation to all these other approaches that we have been seeing in the literature?
Do I answer this or do you answer this? I think I can start and Raquel can add a little bit later. Am I being heard all right? Oh,
yes, perfectly.
Yes.
Yeah. Well, first, I think that usually when this topic is discussed, many of the solutions come as a really commercial, really, how do I put it? Really expensive solution. And one of the key points that we wanted to bring into the design was accessibility, was using the materials that are already common to the local context. We, in conception, tried to think about, which didn't translate as well, but it was in the path of concepting the design, was how do we manage the pipeline of material and having that not be complex, because when you work with modules, the more modules you make, the more complicated you have the final element being. It increases the expenses. So we try to reduce the number of modules to the least possible. The frame is one type of frame, the element is one type of element, and the key was how we can distribute it and how we can make it how we can make variations that perform differently to that determined context, and we build a library that we can apply to that facade. That was the first main thing, I assume. That is the main thing. I don't know if
yeah
no,
that's great.
There's also the way we because when we work on this, we are already used to having Grasshopper to take in sunlight data and interpret it, but I assume that that's not something that happens a while. So I think a lot. So I think that can be considered innovative in a way.
Yeah, that's great. It's a smart way to do it in a, making these different combinations in order to keep keep costs low, right? Okay, so I think that Marcela also has some questions for the other presenters.
Yes,
right, Marcela?
Yes, I do. Maybe I'll start with Yang Song, my order of the videos. So this is very interesting. We have two papers that we're dealing with. How do you increase access to robots, to robotics, for architects, for people that don't have so much of a background in programming. So I just wanted to understand Yang Song's software, right? The software methodology he's using. So what exactly are you controlling when you're using this AR workflow? Are you controlling only the positioning where you begin to use a pre-programmed code for the robot? That was a little bit lost in the paper. I didn't really understand what's the extent of the control of this real-time control you have over the robot.
Because I just started to do this research. So for now, it is like you can control the point you want the robot to move, and you can also control the end effector functions like peak or release. And you can also use your AR code or use your mobile phone to point or draw the robotic trajectory. So it's kind of, I will explore that in the future for more functions and for more operations. So for now, I can only achieve to point out the points for the robotic to move, and also like the position and conversion rotation, and also the trajectory and the simple pick and place operation.
Okay, I understand. Well, this is very interesting. You're basically removing the numeric control we would have when using a pre-programmed code, and you're like making it an extension of your arm, basically. Is that it?
Yeah. Because all the progress and the system, I already pre-coding them in the Grasshopper. So for the user or for somebody who lack of this kind of knowledge, they can just interact with the AR interface. So they don't need to know anything behind the interface. They just need to play with them. Yeah.
Got it. Thank you. I think Leonardo has a question. Is it for Yang Song also?
Yes, for Yang as well, right?
Please go ahead.
Yes. When in your presentation you spoke of recognizing the environment in order to place the arm for it to operate, and I understand the question has many facets. Let's put it this way. The thing is, first, I see you used surface recognition. Is it 3D scanning and photogrammetry?
You mean the environment mesh scanning?
Yes.
Yeah.
How is it done? Yeah.
Yes, you can use like two methods. Before we have the augmented reality technology, you can use the camera scanning the environment. But for now, they already upload the camera, and they have the camera on your headset. So you can just use like the HoloLens headset to scan the environment and just output the 3D mesh into the Grasshopper. Or you can use your mobile phone, like I think above iPhone 11, they have the spatial scanning function.
The LiDAR.
Yeah.
So please finish. What does it?
Yeah, but the like the accuracy, the HoloLens camera is better than the mobile phones. So yeah.
Oh, so the second part of my question is difficulties when recognizing the environment, because I understand there are some problems when you try to recognize the environment with reflective surfaces or something of the like. Do you face those sorts of problems in your research?
I haven't fixed that kind of problem, because it's just like a basic research. I'm just doing like very normal surface or some non-complex structures. So maybe in the future, I will facing like different lighting influence or some complex structures. Because when we are doing this kind of research, if the background is too light or too dark, the AR camera cannot detect that. So it is also a kind of research in the future.
I see. So the last thing is, how do you place how do you place the arm spatially on the environment? How does it understand that the arm is on that specific point, and understand that how it relates to the environment?
Like you mean, how can I locate the digital one with the physical robotic arm, the location?
Yeah.
So we have the AR code for you to scan. So you can just place the code on your robotic desk to scan them to locate.
Oh,
Yeah.
I see.
Mm-hmm.
Yeah, that's it. Thank you.
Yeah, thank you.
Yes, if anybody has a question, just raise your hand or just jump in. Does any of the guests have questions?
I can. Oh, sorry.
Yes.
Sorry, I raised my hand. Sorry about that. I was about to ask a question to Yang Song on the same kind of train of thought. How far are we from a condition where we could actually pick up a small robotic arm and a mobile phone and just transport it into an environment and then start playing with it and constructing with it just by using the phone?
Sorry, you mean how far? How far what?
I'm just trying to kind of speculate according to what you've presented, and I see one of the potentials is robotic kits that we can take to a remote location without too much of a hassle and setup, right? So how easy would it be to make, even remove the requirement for an additional camera and just use the mobile phone connected with the robot to control it? So that we could actually create a kit that we could maybe take, I don't know, to schools in faraway places or places where they're not, or a construction site.
Oh yeah, so all the like the application and the functions is done by the plugin. It's called Hologram. So that kind of plugin can help you to make some interface and functions in your mobile phone or HoloLens. So this is a basic function. So all the things you need to do is just like normal programming in the Grasshopper. So I think it's just kind of a file. So if you have the robot, you have the mobile phone, and if you have that file, so you can achieve that. So it's not like a normal application on your mobile phone, but in the future we are planning to make some our own application. But now it's rely on the Hologram plugin.
Okay, thank you.
Somebody
Thanks.
else wanted to say something.
Yes, I think SIGraDi had a question, right?
Yes, sorry. My question is for Theodore for NFTs and the topologies. So you, in other words, you're saying the kits of parts of the buildings or components will be sold out in NFTs with NFTs, and then we will get feedback through this process, if I understand it right, for the circular economy. And so I think this is a very, very, how can I say, great point to underline, since NFT is a very popular, topic right now. And but do you see also some dangers about this, feedbacks or having, clusters all the way? I mean, it's like the constructors and architects, dilemma, and they're so what kind of, outcomes could be occurred? Also, this will have a, cultural or economical impact on the whole subject. So the question is this.
Thank you for the question. That's really interesting. So we have been playing with this technology for the past 3 years, and our objective is to create more tools that are easy to use for architects to either play with, for the research community to advance their knowledge. But also we're trying to create essentially digital infrastructure that will operate between building information modeling, designers, and the supply chain. The dangers that you mentioned are real, in the sense that a lot of the times the concept we are presenting would need for information about a whole building to be recorded on the blockchain to get advantage of the additional information that you record there and then track it. So on the blockchain layer, you need essentially a kind of regulator of information, of who has access to the information, how it has access, and how they pass it on. One of the other essentially prototypes that we have built looks into incentives, and we're working towards essentially building a triangle between the way an architectural designer creates a design, or a series of designers create a design, how they connect with the supply chain, and then how do we incentivize through the blockchain carbon efficiencies and energy efficiencies. So to actually try to make the best possible decisions in terms of that. It is a very complicated problem. It's not easy to solve. And at the moment, we're still at the level where we're creating the first prototypes to validate, to see whether the project is, the concept is realizable. What we want to do at the moment is continue publishing our tools, and then also find new ways where this technology can provide new business models for architects and computational designers to operate with. Because one of the things you can do is you can actually take, for example, the facades that we saw by Leonardo and tokenize them, or tokenize the process they're using. And then every time someone uses the process, the original team will be compensated for creating that. So it's a combination between being fair in terms of compensation, but also open source as much as possible.
Thank you, Theodore. Manfred has a question for Raquel and Leonardo. Can you see it in the chat, or I can read it? How did you use GIS in your research? Who would like to answer?
Well, even though we did not use the context for simulate reflections, for example, we wanted to see if there were blocks or any buildings that could block radiation in our main research object. So we used Edit, the plugin, to place the shapes, the GIS shapes, into Grasshopper, and to make the volumes for the buildings, so we could use it to see if they could have any kind of interference into radiation. Do you want to add anything, Leonardo?
No, I think that's it. I wasn't even actually sure. I had an idea that was mostly to get the context shape of the surrounding spaces, but I wasn't entirely sure it was just that, but it's basically that.
Good. Any other questions by Patricia, Daniel? Any questions? Any comments on the session, on the presentations?
Well, sorry, some parts of the discussions, I couldn't actually listen to them. Some parts, I all watched the presentations. So I have a question for Yang Song. Maybe somebody asked it before, but Yang, have you ever tried real-time, physical simulations via robotics? Or is it just, you are just interested in assembly, phases? I mean, I'm curious about the real-time physical simulations, like seeing through what kind of model or for what kind of insights, if the manipulation through robotic hands, for example.
For now, I just use the assembly part. So maybe the physical, I'm not quite sure what kind of the physical simulation you mean.
For example, with Kangaroo or with Caramba, while creating, I'm also interested in fabric form and computation studies. So the thing is, I have no idea about robotics, though. I'm not working on robotics. Also, that's why I'm asking. Have you ever tried seeing through the Caramba or other physical simulations? It doesn't have to be Caramba. Any physical simulator will be fine with HoloLens. I mean, I just wanted to ask, have you ever tried, if you have any work on it? So that's why I asked.
Cause the structure I designed, so I need to have like a physical simulation for it can to test it can stand or not. So I'm using the physics X. So that is a Grasshopper plugin for you to test. Because my structure is based on the brick system, so it's not like the bin or some intersect lock. So the Karamba and Kangaroo may not works for that. So I use the physics X simulation. Yeah, so you can get that on for right now. Yeah,
Thank you.
thank you.
Yeah, so if you I would like to just continuing on this discussion with Yang Song. Just ask you one thing that I realized that the type of robot that you used is not really an industrial heavy duty robot. It's more like a laboratory, the type of robot that we could have in a typical architectural school laboratory. And so what I found very nice is that you're using this type of more pedagogical type of robot for doing exercise construction. So how would that translate into the construction site?
Yeah, it's also a question I'm thinking right now. So, so for the like the construction robot, they can do more tasks and like very heavy. They can carry very heavy things as more precise than the lab one. Because now I'm doing some works, so the physics tolerance and the digital tolerance they make my outcome not accurate. So maybe in the future I will try, but I don't know my university could give me an industry robot for or not.
Yeah, but at the same time, it's nice that you're being able to do it with the type of robot that you have available. And I'm sure that a lot of people in research in this area, they have the same issue. This is the type of robot that they have available, and we have to start doing something with it and experimenting with this type of construction. So, but then the question now is how to translate what we're doing in the lab into the construction site, right? Yang. So I think it's something that it's probably a common issue that all of us are having now, because at the very beginning, people who were working with robots, they were using these big KUKA robots that are meant for industrial environments. But then they're really much more expensive than the ones that are now available for the lab. And so maybe one important thing is, like you said, this thing that you said that is going to be your next issue, how we translate these technologies, these methods that we develop in the lab into the construction site, or maybe even bring this type of cheaper robots into the construction site. Maybe that's also another possibility, right?
Yeah.
Yeah, great. I don't know if Marcela also perhaps
Leonardo.
had another question.
Leonardo has a
Oh
question.
yes, I just see Leonardo has a raised hand.
Yeah, I'd like to apologize to Yang for the barrage of questions, but I have one more. About you use the HoloLens and the iPhone to scan the environment for obstacles, but does it work in the sense of making an uneven assembly? In the case I have an uneven ground, for example, can I having the information of the ground being uneven, I can make an assembly that's uneven to the ground? Or does it work with two separate things where you have the context just to avoid, and the assembly being a thing itself where it needs a plain ground to be assembled?
I didn't get your.
Oh, I can rephrase it. You said that you need that you capture the context of the environment. You capture the 3D model of the environment with the HoloLens on the iPhone. And in the case of let me see, I want to make an uneven assembly. For whatever reason, the ground, it's not a plane. It's shaped in some oblong shape. and I need to place the objects in that oblong shape to make the assembly. Do I need it to can I use this technology in this way, where having the context of an uneven ground, I can make an uneven assembly to the ground of the whatever I'm assembling with the robot?
Yeah, you mean you want to like assembly in some flat surface. I think you can use this kind of method to do that, but my method is about like during the operation there's some like obstacles for the robotic to avoid that. It's not like playing on some unflattened surface, because I think if you want playing something on an uncertain surface, it is before design, so you need to scan the surface first and then design, and then for the robotic fabrication. So it's like different steps.
Yeah. Oh, I understand. Thanks.
Great. So yes, I guess Marcela had a last question, right?
Last question, yes, for Theo. Just in terms of what his next steps are with his research. So right now, as I understand it, you're working with the end of a life cycle for a building and the beginning of the life cycle for another one. Do you see NFTs as a possibility, for example, for managing the life cycle of a building in terms of maybe its carbon footprint, energy consumption, carbon credits? I don't know.
So thanks for the question. Yes, we're looking at the whole life cycle. So we're looking at essentially, right now we're looking at the moment the design for the building gets created. Which on practical terms, I mean, if you're in Europe, everybody will tell you, well, that's not really useful. 80% of the buildings have already been built. How do we get information from the existing buildings into a system like that? So that's one of the open questions we have, right? How do you scan the already existing potential of materials that you have in existing buildings? How do you decide which one is to be recycled and which one is to be kept, which is always gets for a passionate architectural argument. And essentially what we're trying to build is connectors between building information modeling and all of those processes. So at the moment, we're still building the first tools. We just managed to make it totally visual this year, and hopefully by publishing them, we'll get more researchers and users on them, and we'll get even more ideas.
Great, thank you. And good luck. So wonderful topic.
Thank you.
Yes, very relevant to the world nowadays, I guess. Mm-hmm. Okay, so I think we have come to the end of this session, and I would like to thank all the presenters who participated. I answered all the difficult questions. I hope this discussion can help you proceed with your work, and I would like to thank also all the guests, and especially Marcela for co-sharing the session with me. It was really a pleasure seeing you all from all different parts of the world. I don't know which time you have at your places right now, but so have a great afternoon, evening, or morning, wherever you are. Thank you so much for attending.
Thank you, guys.
Thank you
for the great discussions.